Okay, 2.1, which is what we covered last time, was all about sets, and we learned how to represent sets with our curly brackets, what exactly sets mean, and today we're going to do a little bit more with sets. Chapter 2 is all about sets, so you're going to keep using them, but we're going to talk more about the complement of sets and subsets and things like that. So we've got a few definitions to get started with. That way we understand what it is we're talking about when I talk about the universal set or the complement of a set. So the universal set will always be indicated with a capital U, and that is simply the universe of discourse, aka what is all the stuff we're talking about at that time. So that's going to change from problem to problem because what we're discussing is going to change. Sometimes our universe is going to be all types of cars, or our universe will be all whole numbers, or our universe will be the alphabet. It just depends on what the problem is talking about. But your problems are very specific. Even on Pearson, they give you a U set, and it will list out all the elements, or it will specify what those elements are that live within that universe, so you understand what it is we're actually talking about. So the universal set is just the biggest group that we could talk about in terms of our problems. And then, as we saw last time, sets are just simply a listing of elements. So if I'm talking about, in my universal set, all of the even numbers between 0 and 10, that's the numbers 2, 4, 6, and 8. So there's only 4 elements in that. So then I could talk about a set A, which has the elements 2 and 4 in it. That lives within our universe. So we can talk about that. We can talk about complements of these sets as well. So the complement of a set states that for any set A that lives within the universal set, the complement of A, which is written as A prime, or A with that little dash above it, is the set of elements in U that are not in set A. So if we write this out with our set builder notation, the complement of set A is the set of X such that X is an element of the universal set and X is not an element of A. That's how we would read that. Math is really cool in that we have all these nice little symbols where I can write that all out right there on that one line, and that would take me 2 or 3 lines if I used all the words that I just spoke. So I'll speak them again. The complement of A is the set of X such that X is an element of the universal set and X is not an element of A. So when we look, this is why we have to know what the universal set is, because we can't determine what the complement is of a set if we don't know what every other element is that is not included in that set. And so they have to tell you the universal set, and then you'll be given an A or a B or a whole bunch of different sets, and you'll be asked to determine what these are. So the picture that is drawn here is kind of a general representation of the universal set is the big box. A is a set within the universe. And then A complement is just outside of that circle because it's going to be all these other elements that live in the box that don't live inside the circle. That's what it means. So our universe is M&Ms. The ones inside the circle have nuts. All the ones outside have no nuts. So those are the caramel ones or the cookie crunch ones or the mini M&Ms. But the ones that have almonds and peanut butter and peanuts, those all live inside the circle. All of them are M&Ms, and we're just differentiating between the M&Ms. So the universal set over here is the set of X such that X is an element of A or X is an element of A complement. When you combine A with A complement, you will get the universal set because that includes everything. Are there any questions on the universal set or the complement of a set? Okay, let's do an example. You can't see that, so we'll slide up. Try to keep the picture up there and get this first example up there as well. This is an example just like one that's in the homework problems. That's why I like to do them. It says, let our universal set be the set of A, B, C, D, E, F, G, H. So like the first half of the alphabet pretty much. We're going to let M be the set A, B, E, and F. And we're going to let N be the set B, D, E, G, and H. I went through all of the homework problems this morning. You have ones that are very similar to this. Then it asks us to find M complement. So when we are asked to find the complement, what we're going to do is we're going to look at the universal set, and we're going to say, okay, what lives in this universal set that doesn't live in M? Because if it lives in M, it can't live in M complement. So I'm going to go down the list. I have A, B. Well, C lives in the universe but doesn't live in M, so it's got to live in the complement. D lives in the universe, doesn't live in the here. E, F, and then there's G and H. So you are simply listing the elements that live in U that don't live in M. That is M complement. So what lives in N complement? A, C, and F. Yep, if I look here at what lives in N, I'm just going to look for what doesn't live in N. So that's A, then I have B, C, D, E, and then F is the only last one. Questions on how this works? Okey-dokey. So there's a couple of things to note. The big one is that if you think about finding the complement of the universal set, you're always going to get the empty set because nothing lives outside of the universe. We're only considering things in the universe, so the complement of that is the empty set or the null set. Inversely, the complement of the null set is the universe. Remember, the null set is the set of things where there's literally nothing in it. 0 is a number. Yes, it represents nothing in terms of mathematics, but it is an element. So if you have a set that contains the number 0 and that's the only thing in it, that is not the same thing as our empty set. Our empty set literally has nothing. So, always good to note that. So, we've talked about the universal set, we've talked about the complement. So let's talk about subsets. See the little picture over to the side. I might have to scroll out a little bit. There we go. So a subset of a set is such that set A is a subset of B if every element of A is also an element of B. And we write that as this little c with a line underneath it. A is a subset of B. Everything that lives in A has to also live in B. And that little diagram to the left kind of indicates that. We have our universe, we have this set A, and notice all the way around set A is set B. This looks a lot like the diagram I had in 2.1 where the different types of numbers And in the very center of our types of numbers was our counting numbers. Those were the numbers 1, 2, 3, 4. That was our inner circle. And then right outside of that circle, we had our whole numbers. That included all of our counting numbers and the number 0. So B can have more elements than that lived in A, but everything that's in A has to live in B. That's why it's totally encircled by B. All of our counting numbers were also whole numbers, but it didn't work the other way. I couldn't say all whole numbers are counting numbers because there's the number 0, and 0 is not a counting number. So some of your problems are going to be about deciding whether or not two sets are subsets of each other or not. And when they list out all of the elements, what you're really checking for is you're going to be checking to make sure that the first set, that all of those elements live in the second set. If they don't give you all of the elements written out, they're going to give you enough information. Like the first set is all peanut M&Ms, and the second set is all M&Ms. So are peanut M&Ms a subset of M&Ms? Yeah, because they're still M&Ms. So we're going to do 3 examples. But it looks like you're only going to get to see one at a time for a minute. There's only so much space over here. Maybe 1.5-ish. So we're going to write either subset or not a subset to make these statements true. Whenever you see a slash through something, that means it negates it. So we need to determine, is set 3, 4, 5, and 6 a subset of 3, 4, 5, 6, 7? Is there anything that lives in the first that doesn't live over here? And the answer is no. So that means that our first set is a subset of the second set. And hopefully you can see that it does matter the order. If I had written these the other way, if I had written set 3, 4, 5, 6, 7, and then the line, and then set 3, 4, 5, 6, then I would be writing is not a subset because this has the number 7 in it, and this one doesn't. So the order that they present your sets to you is very important. Now, the order that they give you for your sets is important, but the order that the elements inside your sets is written is not as important. The only thing that matters is that all the elements represented in the first set are represented in the second. So here, the very first set of B is 5, 6, 7, 8. They're in numerical order. But when we look at the second set, it goes 6, 5, 8, and 7. The order is out. That's okay. The order doesn't have to be the same. The fact that we have a 5 in both, a 6 in both, a 7 in both, and an 8 in both, that means that it still works. The first one is still a subset of the second. And then for C, we have the set 1, 2, and 6 compared to 2, 4, 6, and 8. This first one has a 1. That is not represented anywhere else over here. So our first set is not a subset. Are there any questions on how we determine if something is a subset of another? All right. Back in 2.1, we talked about set equality just for a brief moment. It was one of the definitions that we had. Don't look up here, you're going to get motion sickness while I move it. Set equality, as we defined it in 2.1, meant two sets could be equal if and only if all the elements that lived in A also lived in B, and all the elements that lived in B also lived in A. But now that we have this concept of subsets, we can actually shorten our definition of set equality and make it a little bit simpler, where we can say set A equals set B if and only if A is a subset of B, which means all the elements that are in A live in B, and B is a subset of A. So all the elements of B live in A. It's saying the exact same thing that we said in 5.1. It's just now we're talking about it in terms of subsets. And it made it from like a 3-line definition to a 1-line definition, which is always nice. Now, we talked about subsets, but there's also a thing called the proper subset. The proper subset is a subset that is not equal to the entire whole. So if you look at this symbol here, our subset symbol, notice it's got that little C with a line underneath it. That looks a lot like a, can you see this? Yes. Like a greater than or equal to or less than or equal to. That's just an inequality symbol that we use in math. But it has this line underneath which means equals to. And that's what this line up here in subset means. It means B can actually be all of A. We saw that on our, let's see, on our second example here with subsets. These two were equal. They were the exact same sets. So it's not really all that fun to say this one's a subset of this one because it's the entire set. And so in order to be a proper subset, A would be a proper subset of B if A is a subset of B and A does not equal B. So to be a proper subset, you are smaller than it, but you're not all of it. And so you'll notice our symbol changes a little bit where we drop that equals to aspect of our subset sign so that we have just A, kind of little c, B. There's no line underneath it. So proper subsets will not be the entire set. Because oftentimes thinking about the subset as the whole, it doesn't really help us a ton. We want to look at smaller subsections. So there's two separate notes here. It says the empty set is a subset of B for any set B. I don't care what universe you want to talk about or what set you want to talk about. The empty set is going to be a subset of it. Every time. But the empty set is not always a proper subset of B. The empty set is only a proper subset of B if B is not the empty set. Because if B is the empty set, then it's not a proper subset because that's the entire universe. Some of your problems are going to give you sets, and it's going to ask you to list out all the subsets for these sets. And so it's important to note that whenever you start with these, the entire thing can be a subset, but the entire thing cannot be a proper subset. And the empty set will always be one of the options. Oh, there's another note. Every set except the empty set has at least two subsets. The empty set and the set itself. If you are the empty set, you only have one subset, the empty set. That's why it says except the empty set. So if you are given the set and it has only one number in it, let's say number 1, and you have to write out all of these subsets, you will have the empty set and you will have the set of 1. You have two different subsets. And we're going to do 3 examples where we list out all the subsets. These can get kind of tedious, listing out all the subsets. And so we're going to find some neat little tricks to find the number of subsets without having to list them out. but we're going to kind of see a pattern emerge by listing out all of the subsets. Okay, I'm going to scroll up. So we can list all of the subsets. And we'll do the first two, and then I'll scroll up more. So we're going to list all of the subsets for, the first one is just a set of 7 and 8. There's only 2 elements in that set, but we have to list all the different breakdowns that we can get from that set. Well, the note above says every set, as long as it's not empty, has at least 2 subsets. The empty set and the whole set itself. So that's always where I'm going to start when I have to write out the subsets. I'm going to write out the empty set, and I'm going to write out the entire set as it is. Now this one I can actually get a couple more subsets, because maybe I only want to consider the set that contains the number 7. Or maybe I want to consider the set that contains only the number 8. Are there any other possible ways to list out those 2 numbers? We listed none of them, we listed all of them, and then we listed them separately. That's pretty much it whenever you have 2 numbers, or 2 elements. So there's 4 possible subsets when there's 2 elements. So I'm just going to write that over here as a little note. That's what the 4 means. Now let's look if our set has 3 elements. We have elements A, B, and C. Again, I'm going to start with the empty set, and I'm going to write the full set. A, B, C. And then there's lots of different ways you could approach writing out the remaining subsets. I'm going to start by writing every element in a set all by itself. So I'd have set A, I'd have set B, I'd have set C. Now, what if I want to just pick 2 sets, or 2 elements within the set? I could have A, B. I could have A, C. I could have B, C. I already listed B, A, because the order doesn't matter inside. I've listed B, C. So that should be all of them. I don't think there's any other way to represent these elements. 1, 2, 3, 4, 5, 6, 7, 8. When there was 3 elements, I got 8 subsets. So let's look at 4. We have the numbers 0, 1, 2, and 3. So you can have the empty set. Oops, 0, 1, 2, 3. You can have the full set. We could have each element in a set all by itself. Like that. Then we could have sets that only have 2 elements. 0 and 1. 0 and 2, oops, 0 and 3, 1 and 2, 1 and 3, 2 and 3. But we can also consider 3 elements at a time, because there's 4 in this one. So let's start with 0, 1, 2. I could have 0, 1, 3. I could have 1, 2, 3. And then all of those contain the number 1. So I could have 0, 2, 3. And I think that's all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yep, that's all of them. So depending on the number of elements, you can get a really large quantity of subsets. And it can happen really fast. You notice each time, like we went from 4 to 8 to 16. It kept growing. And if you're sitting there wondering, why are we learning this? What good is this? If you've ever looked at like a Sonic drink menu, it'll tell you that there's 65 million blah, blah, blah different ways you can order their drinks. This is exactly what it is. They have a master list of so many drink options, and the way you combine them determines what drink you're getting. And it's exactly using sets. Because you can order a Sprite with cherry, with nerds if you want. So you're using 3 different options, and that's one of the subsets of their grand option. And this is how they come up with all those. So math does factor into the everyday world. Now, as you see, though, we had 4 elements, and there was 16 different options. So if we were dealing with a set that had 25 elements in it, that gets super tedious, super fast to figure out how many subsets we have if we have to manually write out every subset. And odds are we're going to mess up somewhere and we're going to lose one, and then that doesn't help us a ton. So there's actually 2 different little formulas, for lack of a better word, that help us to identify how many subsets will fall out of a set. There's one for number of subsets, and there's one for the number of proper subsets. So the number of subsets in a set within number of elements is 2 to the n. And we actually saw that here with our examples. We had 2 elements in this subset, or in this set. Well, 2 to the second power is 4, meaning we have 4 subsets. And that's how many we found. And if we look at the number of proper subsets, it's 2 to the n minus 1. And that's because when we think of proper subsets, we don't want to consider the entire set. And so what are we left with? These 3 options. And so when we find the number of subsets or the number of proper subsets, these tell us how many we're going to have. It doesn't tell us what they are individually. And so this is actually how Sonic does it. They didn't sit there and write out all the possible combinations, because oh my goodness, that would drive somebody mad. But what they did is they took the number of elements, the number of options that they have for their drinks, and they raised it to the 2 to the n minus 1. Then they calculated out a number, that's 65 million or whatever it is, and that told them how many proper subsets or proper drink options that they could actually have. But they didn't have to sit there and list out all the stuff. Do we have questions at all on finding subsets or finding proper subsets? Okay, we're going to find the number of subsets and proper subsets for the following sets. I'll see if I can leave these up there. I need to leave less room at the top of these pages so that they butt up right against the notes better. We're going to find the number of subsets and proper subsets of the set 2, 3, 4, 5, 6, and 7. Notice this is asking for the number of subsets. It did not ask us to list out all the subsets. So we don't have to do the empty set, the full set, and all that jazz like we did on the last 3. All we're going to do is find the number of subsets and the number of proper subsets. So we need to know how many elements are in this set. 1, 2, 3, 4, 5. So the n, or the cardinality, for this set is 5. So the number of subsets equals 2 to the n. So n is 5, so this would be 2 to the 5th power, which is 32. So there are 32 possible subsets if we were to list them all out. Now for proper subsets, That's 2 to the n minus 1. Well, 2 to the n was 2 to the 5th minus 1, which is 32 minus 1. So there's 31 possible subsets. Are you required to write all of that out? No. I do whenever I'm presenting notes, so when you go back to reference things, you have them and you're not wondering where I got 31 magically out of the air. So if there's 32 possible subsets, you simply take away the entire set as a whole, and that gives you the proper subsets. I promise on my white paper it does not look as crooked as that, but that's fine. 1, 2, 3, 4, 5, 9, 12, and 14. So that's 6, 7, 8. 8 elements. So subsets again is 2 to the n, so 2 to the 8th. Just with 8 elements in there, you would have 256 possible subsets. That got big pretty quick, and I'm really glad we're not being asked to list out all those. That's what I would do to you if I was a really mean teacher, but I'm not. So proper subsets will be 256, take away 1, because we're going to take away the whole set itself, giving us 255 possible proper subsets.